Okay, thank you so much for the invitation to give a plenary talk at the SBIE meeting. This is actually a very difficult audience to address because there are so many experts in astronomy and cosmology who are much more knowledgeable than I am. And there's such a great group of instrumentalists who know much more than I do about the instrument I'm going to talk about. So all I can do is to give you a little entertainment. So that's the purpose of my talk today. So the title of my talk is Studying the Birth and the Fate of the Universe using Multi-Object Spectroscopy. But this talk is meant to introduce you to a project that's already underway in Japan called Sumir, which stands for Subaru measurement of images in redshifts. So this is a combination of imaging survey and spectroscopic survey being done on Subaru telescope and with a forthcoming instrument that relies on this multi-object spectrograph. So let me start with the puzzle we try to address with this new project. And that's about the way the universe has been expanding all the way since its beginning. So we all know the universe started with this big bang. And with the big bang, everything started to spread out. But as we all know, the gravity would pull things together. It only pulls, it never pushes. So that would actually let all these things that are spread out to being pulled back to each other. And therefore, it starts to lose momentum. And that's what we all thought is the case for many decades. Actually, for 7 decades, we thought the universe ought to be slowing down. But as many of you know, the people actually tried to measure this using the type 1a supernovae. And the end result was that the universe is actually speeding up. That already resulted in a Nobel Prize for the discovery of this new phenomenon, which is dubbed dark energy, because the gravity only pulls, as I said, but if the universe is speeding up, something is pushing. And whatever is pushing, we don't know what it is, but we just gave it a name, dark energy, because it's some form of energy letting the universe to speed up all along. But we don't know what it is, so that's why it's dark, and so that's hence the name dark energy. So that's what we discovered back in 1998, had already been recognized by Nobel Prize in Physics in 2011. And this, I would say, is the biggest mystery in modern physics. Let me repeat, gravity only pulls, but something is pushing the universe today, so that universe is speeding up. And if the rate of speeding up is even further accelerating for some reason, then it might actually come to the point that at some point in the future of the universe, the expansion rate of the universe might become infinite. So the universe gets infinitely ripped apart, and that would be the end of the universe. And for those of you familiar with the modified gravity theory, this can indeed happen in certain theories called Hondesky theory of gravity. So maybe we are really heading to this big rip. Universe might end at some point, infinitely ripped apart. So this is actually what's going on right now. I mentioned that the universe is speeding up now due to something we call dark energy. We don't know what it is. But there are actually 3 phases, as we know it, in the history of the universe, because it starts with also another phase that started with the accelerating expansion of the universe. And this is the phase which is called inflation. And again, we don't know what's causing this inflation, but it was such a dramatic effect that the size of the universe back then was much smaller than the size of an atom, but got stretched to a macroscopic size in almost an instant. The rate of acceleration was such that a bacteria would be as big as a galaxy the next moment. So that's what we believe what happened at the very beginning of the universe. But after this accelerating phase ended, then universe started to behave sort of normally. Gravity only pulls, universe starts to slow down, and that's a decelerating phase of the universe in between 2 accelerating phases. But the reason why they decelerated is also unknown to us, because that's due to the gravity acting on another mysterious form, which we call dark matter. So even though we believe that there are these 3 phases in the history of the universe, first acceleration due to inflation, then deceleration due to dark matter, another acceleration to dark energy, we don't know any one of them. We don't know what caused inflation, we don't know what dark matter is, we don't know what dark energy is, so we learned a lot, as you can see. So, and so that's the way we think the universe had evolved from the very beginning. The universe was smaller than 10 to the minus 26 centimeter when it was born, incredibly small, much smaller than the size of an atomic nucleus. And when the universe was so small, then the quantum physics was important back then. So the universe was undergoing the uncertainty principle, a lot of fluctuations in there. And this fluctuation, we believe, have been imprinted on the cosmic microwave background, the first light coming from the Big Bang, at the level of only 10 to the minus 5 or so. But because that gets stretched to the macroscopic size, that became the origin of the structure today. And the puzzles here is why, when did it accelerate, how did the end acceleration become hot, and what is the theory behind it. And to address this question, my institute is now proposing a new satellite project called LightBird, which is looking for the B-mode polarization of cosmic microwave background, but that's another talk, and I'm going to actually talk about this today. And moving on to the second phase of deceleration, dark matter was the key. And starting from this initial condition, dark matter start to pull with each other. So even though the initial ripple was so tiny, at the level of, let's say, 1 millimeter ripple on a 100-meter deep ocean, it's a very, very tiny ripple, but wherever the dark matter was slightly denser compared to the rest, it pulled by gravity, became a little bit more dense, then gravity becomes more stronger and pulls even further, becomes more stronger, and so on and so forth. At the end of the day, that evolved into the stars and galaxies we live in. So in that sense, dark matter is our mom. We were not born without dark matter, but we don't know who she is. So that's the mystery we try to solve. So one of the things we'd like to address with the multi-object spectroscopy is to really try to see that this indeed happened. So by using the technique called weak gravitational lensing, we can map out distribution of dark matter at the different redshifts. And using the spectrograph, you can determine redshift as well. So you can do actually a slicing of the universe and see how dark matter distributed as a function of distance from us to really tell that it was much more uniformly distributed earlier on, and it is now clumpy as we see in the universe today. So that's something we can prove with this kind of instrument I'm going to talk about. Again, we'd like to know who she is. Dark matter is a mom, separated at birth. We never met her. We'd like to thank her. We'd like to understand who she is. And the third stage is this accelerating expansion. And of course, we don't know what is causing it. Some people even argue that Einstein might have been wrong to lead us to this conclusion. And if we're heading to this big rip, that's a hypothesis. We don't know if that's true. But even the galaxy would eventually get ripped apart because the universe starts to expand at an accelerating pace. Everything is sitting on that accelerating space, so everything starts to get ripped apart. And eventually, we would not see any galaxies anymore because they are torn apart into individual stars. So this video clip was made by a Japanese TV station called NHK, which is sort of the analog of BBC in Japan. And when they actually heard of this story about the big rip, they got really fascinated, and that's why they tried to make a show out of it. So I'm going to also show a couple more video clips about what big rip might do. I apologize ahead of the time. That narration is Japanese, but I try to actually tell you what it says. So this is what would happen to the galaxy. The next video is what would happen to a star, like our sun. So here we go. So this is the situation, what would happen only a couple of hours before we head to the big rip, if it does happen. Then, so the star's going to explode because star itself also gets ripped apart. And I warned them many times that there's no air in the space, so there can't be any sound, but they do put this kind of sound effect. It's a very wrong thing to do. And if it goes further towards the big rip, just like a seconds before, then everything gets ripped down to the level of elementary particles. The stars get torn down to atoms, atoms get torn down to nuclei, nuclei get torn down to protons and neutrons. So that's what would happen at the big rip, if it happens at all. And of course, we don't know if this is true yet. So clearly, if you look at this kind of video clips, the dark energy really does sound like something pretty evil. And something evil seems to be happening right now, right here. Looking at the map of Europe, might be going that way. It may get further ripped like this, which may further undergo another big rip going on, right? So we'll see what happens. So that's why we care about the fate of the universe today. So just sum this up. The view of the universe today is really, really strange. We used to think that everything is made of atoms, but we now know the atoms comprise only about 5% of the universe today. But as the universe gets bigger, if the universe becomes twice as big, volume gets 8 times bigger, and atoms, of course, will thin out 8 times. We don't know what dark matter is. That's about 25% of the universe today. Even though we don't know what it is, it's a form of matter. So if the universe becomes twice as big, the volume 8 times bigger, it does also thin out 8 times. But dark energy is even more mysterious. It comprises about 70% of the universe today. But if the universe becomes twice as big, volume 8 times bigger, it seems to become 8 times bigger. It keeps wetting out of nothing, and that's the behavior of dark energy as we can see it. And that's why we have no clue what this thing is. But the key question here is, does it really go with the volume? Does it become 8 times bigger? Or maybe it's actually only 7 times bigger. Then the dark energy, even though it's speeding up the universe today, is sort of losing its momentum. So maybe the universe will turn back into a decelerating expansion. It may start to slow down again in the future. On the other hand, if the dark energy multiplies by 9 times, the faster the volume, and that would head us to this big rip we just talked about. So what we need to do is to do as precise measurement as possible. How exactly is dark energy multiplying? How exactly is the universe speeding up, so that we can forecast the future of the universe, and that's the purpose of the kind of project I'm talking about today. But whether we are heading to the big rip, or we do eternal accelerated expansion, or we also head back to the decelerated expansion later on, one thing is clear. We can observe all these faraway galaxies today, many of them billions of light years away from us, but all of them are speeding away from us at an accelerated rate. So what it means that over time, we completely lose their sight. We can still observe maybe some of the stars within our Milky Way galaxy, but no other galaxies in our sight. And that would be a very unfortunate thing for this community, because the only time we can observe these faraway galaxies is today. So I've been arguing with the Japanese government that they should give us funding as soon as possible. And they listened to me. So that's how we started this project I call Sumir. So you'd like to use this Subaru telescope, which is a fantastic telescope on the Mauna Kea on the big island of Hawaii. It's a major survey program. Because what we would like to do is understand the trend of the universe, where it's heading to, right? And if you don't understand the trend of a country, you don't want to talk to random people. You don't go to school to talk to only young people. You don't go to hospital to only talk to old people. You need to understand this entire trend of the universe by doing a census. And you don't want to do referendum, because that's by definition a biased sample of people. You want to do an unbiased census of the universe. And for that purpose, you need to have a very large field of view so that you can do this within the time that's imaginable for a graduate student to get a PhD, of course, like 5 years. And for this purpose, Subaru is really fantastic because of the large field of view, the largest one among all the 8 and 10 meter class telescope. And as a matter of fact, it's about 100 times bigger than the Keck, about 1,000 times bigger than Hubble Space Telescope. The first stage that is happening as we speak in an imaging survey with a new camera we built called Hitoshi Prime Cam. It has nearly 1 billion pixels. We like to image many hundreds of millions of galaxies, and we already secured 300 nights on the Subaru telescope. And the next instrument is the multi-object spectroscopy I mentioned earlier. Name of the instrument is Prime Focus Spectrograph, or PFS, which is maximally confusing as PSF. I apologize for this. And it would actually have a 2,400 optical fibers, each controlled by a little robot called Cobra. It would like to measure about 4 million redshifts using this instrument, and we hope to acquire also 300 nights on the Subaru telescope, and this will be a fantastic combination. The Sloan Stereo Sky survey has been extremely successful, as everybody here knows, but that was done on a 2.5 meter telescope by combining imaging and spectroscope survey. We'd like to do this now on an 8 meter class telescope, and that will be much deeper and have much more data coming out of this project. So the imaging survey has these partners, and the spectroscopic survey have even more partners to come in. And here are some parameters. I'm going to actually go through this in detail, but the camera has 5 filters, GRIZY, so it goes into near infrared, and would cover a large area with a big volume because of the large size of the telescope. And this is the wide field corrector lens system that have been already mounted to a camera, and that's already on the Subaru telescope taking data. And this is the array of CCDs on a focal plane. And the performance is fantastic. This is the same field taken by Hubble Space Telescope and also the Subaru telescope. And clearly, Space Telescope would do better in terms of quality of images because of there's no interference from the atmosphere. But you can tell that the Subaru actually isn't too bad. It's actually a very nice image quality, sometimes even going to a half arc second of seeing. And the more important thing here is that for a Hubble Space Telescope, it took them 500 hours to cover this area in 640 orbits, because its field of view is so small. Compared to that on Subaru, it took only 2.5 hours in 3 colors. So this really demonstrates the survey power as well as the quality of images taken with this new camera. And the next thing is spectrograph. I mentioned some of these parameters already. It has 3 arms for spectrograph, covering blue, red, and near-infrared part of the spectrum, relying on Hamamatsu chips as well as teledyne chip. And it's a complicated instrument. So we already do have this wide-field corrector lens system, as I showed a picture of. And out of this, the prime focus area, what you do is swap the array of CCDs by the array of what we call the fiber positioner. That's actually this instrument here. And this is actually a test bench for these fiber positioners called carburers to make sure that there's no collisions and a single board can operate all of them together and so on. And I learned it only yesterday that the carburer in this country means actually this, which says impossibly smooth, and that's exactly what this carburer is about. They are supposed to be impossibly smooth, have 2 disks at the tip that controls the position of the optical fibers, and it is meant to cover the entire patrol region by the motion of these two other disks, and with accuracy within 10 microns or so, and you need to position each of these fiber in a period shorter than 1 minute or so, and we are testing this performance right now. Okay. And each of the optical fiber is actually has another element glued at the tip, its tip, what we call the micro lens, because the Subaru has the f ratio of 2.2, which is, if you imagine a focal ratio degradation, that's actually pretty scary, that you might start losing light in the into reflection within fiber. So we would like to actually change the f ratio by gluing this micro lens at the tip of every optical fiber, which is very labor intensive. That's what we intend to do. And this is a test of the fiber connectors, some optical elements, corrector lens, and the dichroics. And this is the way we've been assembling the camera, the first camera for the spectrograph, and putting together a cryostat for each camera. And this is the prototype of a metrology camera that is supposed to go to the Cassegrain point. So this is a rather complex system, but this is what we are doing right now. And so far, it's been going actually very well. This is the projected throughput of the spectrograph, and for most of this range of the wavelength, it actually exceeds 20%, which is actually a fantastic performance for a fiber spectrograph. And using this kind of instrument, you can measure the redshifts of individual galaxies. Some of the things we'd like to do is focus on these emission line galaxies by O2 emitters, and requiring very high signal-to-noise ratio with a typical 15-minute exposure in each field. We can measure the redshift of many, many galaxies, that you can look at the statistical ensemble and compute its power spectrum, and you can observe these acoustic peaks as observed in cosmic microwave background in a distribution of galaxies. And using these acoustic peaks, their locations would provide us what is called a standard ruler, namely that will give us a very precise measurement of physical distances at the very large scales. And the amplitudes would tell us how the dark matter produced individual galaxies. And together with the combination of the imaging survey that happens prior to this one, we would have measured the bias, how dark matter can produce galaxies of each type already. So you can use also information of this amplitude to extract various cosmological parameters. And using this technique, we can come up with a completely model-independent measurement of how dark energy comprised the total energy density of the universe as a function of the distance from us today. And so what some theory might actually suggest is solid curve, some other theory might suggest is dashed curve. And with this level of accuracy shown in these boxes, you can do a discrimination among many different possibilities of the nature of dark energy and therefore the fate of the universe. You can also do a test of the Einstein theory of relativity at very large distances, and nicely combining this near-infrared capability together with what is going on right now with the Sloan Sky Survey, you can do an uninterrupted test of the gravity theory as a function of redshift. And in addition to this cosmology project, you can also do other kinds of science as well, which is also quite exciting. Again, because of this near-infrared spectrograph, you can cover this entire range of galaxies using emission lines. And this area has been particularly difficult for many surveys in the past because of something called redshift desert, namely that there are no useful lines in optical wavelength in this redshift range of 1 to 2 to be covered by a typical spectrograph. But if you can also rely on near-infrared spectrograph, you can cover this area also in an unbiased fashion. And this area is particularly interesting because that's at the height of the stellar formation activity, so that's another area of science we are very excited about. We can also study nearby objects, like dwarf galaxies nearby, and using this, again, many number of fibers and the large size of the telescope, you can map out the radial velocity of many stars in dwarf galaxies, which is a very important subject for the study of the nature of dark matter, because the way these the stars move are in the gravitational potential created by the dark matter, and how dark matter is distributed would tell us something about how often they might annihilate and produce gamma ray signal, as studied by the Fermi satellite. So that's another subject of this instrument, where you can start to actually get more information about the nature of dark matter, in addition to nature of dark energy. So that's basically the project. There are, of course, many other the projects underway on the building multi-object spectrograph, but I really would like to highlight this point that Subaru is 8-meter class, while many others are 4-meter. And this one is also 8-meter, but the field of view is much, much smaller by an order of magnitude compared to Subaru. And combining this large aperture and the large field of view, we would have a very large survey and a census of the universe as we would like to do it. And there are many other talks at this conference, and I'd like to draw your attention to them. That Naoki Tamura is the wonderful project manager for this the PFS instrument, and he's going to give a talk in the afternoon of the 29th. And there are many other posters presented during this conference, so I hope you wouldn't miss them. And this project is nearly completely funded, except that we are still missing about a few $1 million. The whole project size is about $80 million, so we are almost there, but not quite. So we are soliciting donors and potentially new partners, so we created a promotion video. So I'd like to run that for you. So this is about the nature of dark matter. And this is about the nature of dark energy. And this is how our Milky Way galaxy system had been assembled. And it's actually incredible to watch this video, thinking about these photons coming out of the galaxies billions of light years away. They, just by pure chance, happen to find a Milky Way galaxy in a solar system. Look how aligned the planets are, which is incredible. And then eventually you find the big island of Hawaii. Here is the Subaru telescope, the dome opens. Here's the 8-meter aperture of the telescope mirror. They bounce back into this individually controlled fiber by the Cobra systems. And they pass through the, to the other room after about 50 meters of optical fibers that manufactured to have a good throughput all the way through. And here are the 3 arms of the spectrograph. And by looking at these emission lines and absorption lines, we would like to learn a lot about what's going on in the universe today, also in the past, and also in the future. So that's the project, unveiling the mysteries of the universe. And if anybody is willing to chip in, I'm going to pass out a hat later on. So please contribute the project. Anyway, so you see, the PFS really rocks. Thanks for attention.